The asteroid Bennu is not what you think. Almost everyone who studied this rock got it wrong, because everything scientists assumed about Bennu before we actually reached it turned out to be false. This is not a solid, predictable chunk of stone drifting quietly through space. Bennu is something far stranger. It is a pile of rubble held together so weakly that a spacecraft nearly sank straight into it, like dropping a stone into water. It throws pieces of itself out into space for no clear reason, and somewhere in its future, there's a small chance it collides with Earth. Bennu is the most studied asteroid in human history, and yet almost every single certainty we had about it collapsed the moment we got close enough to touch it. This is the story of how a NASA spacecraft flew millions of kilometers to visit a rock everyone thought they understood, and instead found one of the strangest objects in the solar system. So, let's dive in. Bennu is a near-Earth asteroid, a leftover chunk of material from the very formation of our solar system, over 4.5 billion years ago. It is not massive by asteroid standards, but it is still an imposing object, roughly 500 meters across. For a sense of scale, that is about the height of the Empire State Building, just quietly tumbling through space near our planet. Now, here is the detail that got everyone's attention. Bennu has a small but real chance of colliding with Earth sometime around the year 2182. That is not a reason to panic, but it is exactly why NASA chose this rock, out of the millions of asteroids out there, as the target for one of its most ambitious missions. If we are ever going to defend our planet from something like this, we first need to understand what these objects are actually made of. And based on decades of observations from telescopes here on Earth and in orbit, scientists thought they already had the answer. The data suggested a smooth surface, fine grains of dust and sand gently coating the asteroid, almost like a beach stretched across a rock in space. It looked like the kind of place a spacecraft could land on easily and scoop up a sample without any trouble at all. So NASA built a mission to go find out for certain. What they discovered when they arrived would shatter almost everything they expected. The spacecraft sent to investigate was called OSIRIS-REx, launched by NASA on a mission to travel to Bennu, collect a physical sample of its surface, and bring that material back home to Earth for study. It was a journey of years and millions of kilometers, all building toward one critical moment: arrival. In December 2018, OSIRIS-REx finally reached Bennu and got its first close-up look at the asteroid. And what the team saw was nothing like what they had prepared for. Instead of a smooth, sandy beach waiting patiently for a spacecraft to land, Bennu's surface was a chaotic wilderness of boulders. Massive rocks were scattered everywhere, with barely any of the fine, soft material scientists had been counting on. "We expected some boulders," one mission scientist admitted, "but we anticipated at least some large regions with smoother, finer regolith that would be easy to collect." Instead, it looked like it was all boulders. The team was, in their own words, scratching their heads. But that wasn't even the strangest part. As they studied the asteroid further, they noticed something even more bizarre. Bennu was ejecting small particles of rock off its own surface and out into space, all on its own, with no clear explanation for why. Every single assumption the team had walked in with was already falling apart. And this was only the beginning. Because just as the team started puzzling over the boulders and the flying debris, they realized something else didn't add up at all. Old data from years earlier was telling them something completely different about this asteroid. Back in 2007, more than a decade before OSIRIS-REx ever arrived, NASA's Spitzer Space Telescope had already been studying Bennu from a distance. It measured something called thermal inertia, which is essentially a way of tracking how quickly a surface heats up under sunlight and how quickly it cools back down once that sunlight is gone. Think of it this way. A sandy beach heats up fast under the sun and cools down again almost as quickly once night falls. But a slab of concrete behaves completely differently. It holds on to that heat long after the sun has set, slowly releasing it back into the air. Spitzer's reading of Bennu matched the beach. Low thermal inertia, rapid heating, rapid cooling, exactly what you'd expect from loose, fine sand. But that directly contradicted what OSIRIS-REx was now seeing with its own cameras. Giant boulders, not sand. And boulders should behave like concrete, holding their heat well into the night. Two completely different datasets, describing two completely different asteroids. So which one was Bennu actually telling the truth? One early theory offered a possible explanation. Maybe those boulders weren't solid at all. Maybe they were unusually porous, riddled with tiny air pockets, almost sponge-like in structure. If true, that could explain why they lost heat so quickly, despite their size. But there was only one way to know for certain. Scientists would need to get their hands on an actual piece of Bennu. In October 2020, OSIRIS-REx finally attempted the moment the entire mission had been building toward. It descended toward a site on Bennu's surface nicknamed Nightingale, ready to perform a quick touch-and-go maneuver, tapping the asteroid just long enough to grab a sample before pulling away. Every simulation, every test run back on Earth had predicted the same outcome. The surface would be firm. The spacecraft would barely leave a mark, maybe a small divot, nothing more. That is not what happened. As OSIRIS-REx made contact, it didn't tap the surface. It began sinking straight into it. The asteroid offered almost no resistance at all, and the spacecraft just kept going deeper and deeper into Bennu itself. By the time we fired our thrusters to leave the surface, one scientist later admitted, we were still plunging into the asteroid. For a few tense moments, there was a very real possibility that OSIRIS-REx could become stuck, or worse, disappear entirely beneath the surface of the asteroid it had traveled years to reach. It was only the precisely timed firing of its thrusters that pulled the spacecraft back out before it was too late. As it retreated, cameras captured an enormous wall of debris exploding outward from the impact site, rock and dust flying in every direction. Back on Earth, the mission team watched in stunned disbelief. We saw a giant wall of debris flying away from the sample site, the mission's lead scientist later said. It was really frightening. When the dust settled, the damage told its own story. The spacecraft had gouged out a crater 8 meters wide, roughly 26 feet across. Every single lab test back home had predicted something a fraction of that size. Something about this asteroid was fundamentally different from anything scientists had prepared for, and they were about to find out just how different. Here's what scientists eventually figured out. Bennu's surface isn't solid at all. The particles that make it up are so loosely packed and so weakly bound to each other that the whole surface behaves less like rock and more like a liquid. Imagine stepping onto Bennu yourself. You wouldn't feel solid ground beneath your feet. Instead, it would feel like stepping into a pit of plastic balls, the kind found in children's play areas, where your foot just keeps sinking with almost nothing pushing back. If Bennu was completely packed, that would imply nearly solid rock, one scientist explained. But we found a lot of void space in the surface. That void space is the key to everything. The material isn't tightly compressed like a boulder or a slab of concrete. It's full of gaps, loosely arranged, barely held together at all. To figure this out, researchers didn't just guess. They ran hundreds of computer simulations, adjusting the surface's cohesion and density each time, until one version finally matched exactly what the spacecraft had experienced during that terrifying touchdown. The conclusion reshaped how scientists think about Bennu entirely. This isn't one solid rock drifting through space. It's a rubble pile, an enormous loose heap of rock and dust, barely held together by weak gravity and faint electrostatic forces. But this discovery only solved part of the puzzle. It explained why the spacecraft sank so easily. It still didn't fully explain that earlier contradiction, the strange heat signal that started this entire investigation. Something else was still missing. To finally solve the heat mystery, scientists needed the one thing no telescope could ever provide: an actual physical piece of Bennu sitting in a lab on Earth. When researchers examined the returned samples, they confirmed part of their original theory. The boulders really were porous, full of tiny gaps that helped explain why they lost heat faster than solid rock should. But porosity alone didn't account for everything. There was still a gap between the numbers. That's when researchers in Japan turned to a laser-based technique called lock-in thermography, striking a tiny spot on a sample and watching how the heat spread outward, similar to ripples moving across a pond. And that's when the missing piece finally revealed itself. The rocks weren't just porous. They were riddled with extensive networks of cracks running all the way through them. To study this without contaminating the samples, scientists at NASA sealed the particles inside airtight containers filled with protective nitrogen gas, essentially giving each rock its own tiny spacesuit. From there, they performed X-ray CT scans, mapping the interior of each particle in 3 dimensions without ever exposing it to Earth's atmosphere. Once scientists fed all of this cracked, porous rock data into their simulations and scaled it up to full boulder size, the numbers finally matched. The thermal inertia lined up perfectly with what the spacecraft had measured out at the asteroid itself. It turns out that they're really cracked too, one researcher said, and that was the missing piece of the puzzle. After years of contradictions, Bennu's strange behavior finally made sense. For the first time, scientists can take what a telescope sees from millions of kilometers away and directly connect it to real rock sitting in a lab, collected from that exact same asteroid. That connection changes everything about how we interpret every other asteroid we observe from a distance. And there's a darker implication buried in all of this. A loosely bound rubble pile like Bennu might not behave like solid rock at all if it ever approached Earth. It could shatter unpredictably instead. As one scientist put it, we're still at the beginning of understanding these bodies because they behave in ways that are deeply counterintuitive. Bennu keeps rewriting its own rules, and that's exactly what makes it so fascinating.